Hi everybody. So I'm going to do problem 108 that people had. This was the one with Usain Bolt that people were having issues with. So here we go. I'm going to show you step by step kind of what I did. All right, so 108 says, I'm just going to do part A because part B is basically a duplicate, and then you can try that again on your own. So it says 108 part A world record was set for the men's 100-meter dash in the 2008 Olympic Games in Beijing by Usain Bolt of Jamaica. Bolt coasted across the finish line with a time of 9.69 seconds. So that would be our total time. We call it T total. If we assume that Bolt accelerated for 3 seconds, so this is part A, I'll call it time A, to reach his maximum speed and maintain that speed for the rest of the race, calculate his maximum speed and his acceleration. So maximum speed and acceleration, that's what we want to find out. Maybe do that in a bit of a different color. Boom, boom, maximum speed and acceleration. So first thing you're going to want to do is probably draw a diagram of some sort. Here's what I drew right here. So these are Usain Bolt at the beginning. Here is right after, so he accelerates for some time in between here. And then once he reaches this point here, he's now coasting at a constant velocity. And I know, so I've split this up into parts A and B. So here, this is part A. And then here, this is part B. So A is when he's accelerating, and B is when he is not accelerating. So in between here, we have some abrupt acceleration happening. And the best way to solve problems like this is to split them into two parts, hence why I'm doing A and B. The total time it takes is 9.69 seconds, so I got that written down there. I know it's a 100-meter dash, so his total distance is going to be 100 meters. That might be useful. And I know that they said he accelerates at a uniform acceleration for the first 3 seconds. So I'm calling TA 3 seconds there. Now, before we get into anything, let's draw a velocity versus time graph and see what that might look like. So at first, Usain Bolt's velocity is going to be 0. So at first, he's going to be here. And then we know he is accelerating uniformly for the first part. So again, I'll just do, I'll draw a dotted line down here, and we'll say this is part A, and this is part B. So for the first part, he's going to move with a uniform acceleration, so he's going to increase his speed, and it's probably going to look something like that. Once he reaches 3 seconds, which is right here, then he's going to coast at a constant velocity, so it's just going to go flat like that. And some things I could get, well, the slope of that graph is my acceleration. And then I also know the area under this graph is the displacement. So you might use that graph as well to help you. I don't think I ended up doing that. Let's see if I need it or not. But hopefully it gives you a visualization of what we're doing and why we're splitting this part up right here into two parts. Whenever you have an abrupt acceleration, you always want to split it into two parts. All right, so next up, this is just coming from my solutions. I'm going to build off this now. Because he is accelerating in part A, I'm going to have a Vovaxed, or yeah, kind of something like that. And here I'm using displacement as opposed to the initial position and final position because it's going to end up being more useful in this case. But I got the initial position right here, or the initial velocity right here. They told me it's basically 0. The final velocity, I don't know, but I'm going to call it VB as opposed to just V because we got multiple V's going on around here. So, and then, of course, the acceleration, and they also gave us the time at which he is accelerating there. For B, I have no acceleration, so really my only variables are the displacement for B, which is different from the displacement for A. These are not equal. And then I've got VB, which VB, the velocity that he coasts with, is going to be is going to be the velocity at which he ends here. So looking back up on the graph there, when he reaches the speed here, VB, he then coasts with that speed from that moment on. So that's going to be useful later on. All right. So what the heck are we doing here? Let's see. I've also got this relation. So basically this is kind of all that they've told us. This is all that they've really told us, is that the initial velocity is 0 and he does it for 3 seconds. They've also told us, though, the total time is 9.69 seconds. So I'm going to, now what you want to do is start drawing relationships. And basically that means generating equations that you can then mix and scramble around with one another. So I know the total time is 9.69 seconds. And the total time is going to be the time it takes for him to go TA plus the time it takes for him to go TB. So if I use that, I can say, well, the total time is 9.69 seconds, which is going to equal TA, which is 3 seconds, plus TB. So I can find TB. TB is just going to be 9.69 minus 3. So that's going to be 6.69 seconds. And I can use that and plug that in there. 6.69 seconds. Awesome. All right, now I need another relationship. Oftentimes I would go to my equations of motion or something like that, but I'm actually going to cut this time in, and you could use equations of motion, but eventually you're going to need to build on this relationship. So to make things a little cleaner, I'm going to start with that relationship, which is the fact that the total distance, or the total displacement that Usain Bolt travels, well, that's going to be the displacement that he travels along A plus the displacement he travels along B. Now I'm going to use that equation of motion stuff. So I'm actually going to use beta, and beta basically says this is the displacement form of beta, that the displacement, so the displacement of, I'll start with A. Well, let's just write down the beta. So the displacement is equal to the initial velocity multiplied by the time plus 1/2 times the acceleration times the time squared. So let's see, write that in for part A. For part A, the displacement is equal to, I know his initial velocity is 0 multiplied by the time plus 1/2 times the acceleration, which is one of the things I'm looking for, times the t, but which t? Is it TA, TB, total time? Well, it's actually TA, because we're talking about situation A, so this is going to be TA squared. And next up, I'm going to get that same thing for B. Oh, this is delta XA, by the way. So for B, it's going to be delta XB, and that's going to equal V, well, who's V? Oh, VB, right? Because he's just moving at a constant speed. So it's going to be VB times T, which time? TA, TB, T total? Oh, TB, because this is now in the B section. This is after he's accelerated. This is over here now. So that's going to be TB plus 1/2 the acceleration was 0, t squared, and 0 times anything is just 0, so all this just goes to 0. And that just leaves me with delta XB equals VB TB, and I should have simplified A. A can simplify to delta XA equals 1/2 A TA squared. All right. And what I'm going to do is we're going to take this, because this is XA, plug it in there. And then we're going to take this, because this is delta XB, and plug it in there. And so let's take all this now and write it again back here. So this is going to be delta X total equals 1/2 A TA squared plus VB TB. Well, I know the total displacement. The total displacement, which I'll plug in a bit, is 100 meters. I don't know the acceleration, but that's something I'm looking for. I know TA, it's 3 seconds. So I know I got it. I want to know this. I don't know VB. And I do know TB. I just found it. It was 6.69 seconds. So if I can replace VB with something that has A in it, then I could solve for this thing. So let's try that. And I would look at my kinematic equations, and the first thing that would come to mind would be velocity. Final velocity of anything at any moment is equal to the initial velocity plus the acceleration times the time. So if I were to do this during part A, use this equation, or you could get super fancy and, you know, take the derivative there. Do I want to do that? No, let's not do that. Let's use the equation. I don't want to get too fancy. Okay. So, okay. I'm going to use all this information now, and so this is all A information to get the final velocity at A, which is actually going to be VB. Because again, like I said before, check out this graph. The final velocity at part A is equal to VB because that's the velocity at which he coasts after that. All right. So this is going to be VB equals V naught, which is just 0, plus the acceleration, that's what I'm looking for, times the time. Whose time? TA, TB, T total. Well, this is all A stuff, so it's going to be TA. And then, I guess just simplifying, VB equals A, TA. So now I can take all of this and plug it in there. So many arrows around here. So let's clean this one up a little bit, see what that gives us. It gives us that the total displacement is equal to 1/2 A TA squared plus A TA TB. And now I can solve for A. So I'm almost done here. I can see that both of these terms has a factor of A in it. So I'm going to pull that out. That'll leave me with delta X total equals A times TA squared over 2 plus TA TB. And there we go. And now I'm going to take all this nonsense and divide both sides by that nonsense so that I can isolate A. So it's going to be delta X total over TA squared over 2 plus TA TB equals the acceleration. So now plugging everything in, my total displacement is 100 meters. Just forego units for clarity. And then the original time was 3 squared divided by 2 plus 3 is TA, and then TB is 6.69. And I could plug all that in, and I'll get my acceleration, which is, let's see, we got 9 divided by 2, 4.5 plus, sorry, I'm doing all this on my calculator, 3 times 6.69. And then lastly, we got 100 divided by all that, 4.07. 4.07 meters per second squared. And that's the acceleration. Now the other thing they want me to get is the maximum speed as well. So how can I get the maximum speed? Well, again, looking at this graph, the maximum speed, well, that's where essentially the final velocity, VB, that he reaches, where he coasts until the end. So I'm going to get VB, and how can I get VB? I can use this relationship again. So I'm actually just going to keep going with this special case solution that I solved for and plug in there. So that's going to give me VB equals the acceleration times TA. I now know the acceleration, so I can solve for this. So VB, that's just going to be 4.07 multiplied by TA, which is 3. So VB, the maximum speed is going to be 12 something. 4.07 multiplied by 3, 12.2 meters per second. And done. So there you go. Hopefully that clarifies things a little bit for you. See if you can do part B. And if you're having trouble, just go check my solutions on Schoology. All right. See ya.